Right, hello. My name's David Ware. I'm going to be talking to you about MQ clusters, some of the features and how you can use them to solve your problems. Start off with just a little bit of why you might get into clusters. We won't go into the low-level details of configuration or things like that here. That can be another session. Then we're going to talk about, like I said, some of the features, like how do you maintain availability of your services through using MQ clusters. How do you route messages intelligently? How do you make sure that your system works efficiently? And then finally, we're going to finish up with a little bit about how MQ clusters interact with a disaster recovery setup. So, why might you have a cluster? So, when you start off with MQ, things typically start off nice and simple. Maybe even a single queue manager, you're just using a queue to put messages on, and then take them off again, process them, maybe send a reply back again. So we've got maybe a client-server application, as we've got here. But soon, you're probably going to end up doing routing messages between multiple queue managers. Maybe that's because you've got multiple systems, or maybe because you've got to be able to route between different locations. So that's not too bad. You have to join the queue managers together by defining MQ channels, pointing them at each other, defining transmission queues and some remote queue definitions. But it's not too bad to understand at this point. But as you scale up, you want to scale up your applications, more and more instances of them potentially, and then you've got more applications to bring into your system as well. Once you've got those extra systems, possibly you want to have more queue managers to service them. Maybe for scale, again, maybe it's because you've got a larger estate, a larger network of systems. So we've got more queue managers. To have the more queue managers, we have to connect them with more MQ channels that we define to each queue manager pair that needs to talk. And then we need to define all the extra definitions, transmission queues, remote queue definitions, those sorts of things. So things are getting a bit more complicated here. And then more and more applications come along over time. You lose track of some of them, what some of them are doing, who they need to be able to talk to, where they need to get messages to and from. And then obviously more queue managers come in as well. So you can see an MQ estate can quickly become quite unmanageable from that point of view unless you keep a tight control over what your interactions are between your different queue managers, and therefore which channels need defining and which other resources. So that's where an MQ cluster comes into its own. MQ cluster resolves down to every queue manager effectively needing two channel definitions. It needs a receiver channel to say this is how everybody in the cluster is going to talk to me, and a sender channel to bootstrap you into one of the full repository queue managers. So once you've got that set up, you don't have to worry about remote queue definitions, specific channels between any two pairs of queue managers, because the cluster will work that out for you automatically on the fly and create them for you so that you can use them without even realizing they're there. So that's sort of the first benefit of a cluster, is simplification of your MQ network. But if we zoom in on a particular application, there are other features of an MQ cluster which you can benefit from. So here we've got this request reply application. We've got a client sending in requests, goes to a queue for a service application, and it processes, that sends a response back, and that goes back to the client. So that's nice and simple, two queue managers in this picture. But we might want to scale up that application. We might want to do workload balancing. So if we have multiple instances of that service application, what we can do is we can define an extra queue manager. We can define the same queue as we had of Q1 on that first queue manager on the new queue manager. Now we've got two instances of the same queue in the cluster. When you have multiple instances of the same queue, i.e. it's got the same name, any queue manager that's sending messages to it, that's going to workload balance messages by default across those multiple instances. So now, when a client sends in requests, these purple messages, and sends replies back, you can see that the purple request messages are getting workload balance across the two instances of that Q1. So here we get workload balancing. So now we've scaled up the number of queue managers that can process the messages, which means you can distribute out your service applications widely so that you can utilize more resources. Another thing you can do now is you can add in service availability. If we lose one of these systems, so we've lost that top system, we've now still got one instance left, in which case the queue manager over on the left is going to detect this, as we'll see later, and he's just going to send his requests down to that bottom queue manager. So we've instantly got availability in that if we've lost one instance of it, all the new messages are going to get routed through to the remaining instance. So we'll look at these in more detail as we go through. So we focus in first on availability, that last one. So we're back to the same picture as we had before, but you need to understand where messages can get stuck. If you have an availability problem, what situations do we need to consider? Where are messages going to get stuck in my system, and how do I handle those? So if we see what we did before, we've got our target queues, we've got the request queue over on the right, we've got a reply queue over on the left. And then you can see the dotted queues are cluster transmission queues. So these are transmit queues where messages are temporarily going to be stored while they're being transferred across the channels between these queue managers. So as a message goes through the system, it might be stored on a transmission queue, it might be stored on the target queue before it's taken off by the service, or when the reply comes back, taken off by the client. In all those situations, what's been highlighted are all the points where a message might get stopped in its tracks if we get an availability issue at any point in time. So we need to consider, how do we make sure that any messages that get stuck in any of these positions, how do they get processed? And that depends really on the failure. So if we first look at what happens if we lose a queue manager or a whole host. So we lose that queue manager on the top. Now, we've possibly got some messages stuck, either in the transmission queue about to go from a client's queue manager over to the right top queue manager. So there's some messages stuck. Or we've got some messages stuck on the queue manager itself, waiting to be processed by the service, or even reply messages waiting to come back to the client. First thing that's going to happen though, if we lose a queue manager, the service is going to go down. That service isn't going to be connected to a queue manager anymore, so that's going to become unavailable. If we first look at the messages on the left that are sat on a transmission queue waiting to be sent to that top right-hand queue manager, those messages obviously can't be transmitted to that queue manager because the queue manager is not available, the channel's not going to be available. However, the queue manager on the left detects this because the channel's gone down and knows that those messages could potentially go to the bottom right-hand queue manager because that queue manager hosts the same queue. Now it can only do this if those messages have not been bound to the top right-hand queue manager. So you may have noticed in MQ, when you open a queue, you specify which bind type you want to use, or you leave it up to the def bind option on a queue, the default bind type, and that could be bind on open, bind on put, or sorry, not bind. In those situations, if we bind on open to the queue, we're saying all my messages that I send under this open need to go to one instance of the queue. Which means if I do that at the start of sending messages, and I pick the top left-hand queue manager, sorry, the top right-hand queue manager, then first message will go to that queue manager, and the next one, and the next one, and the next one, they'll all go to the same one. If that queue manager goes down halfway through me sending messages, MQ is not at liberty to reroute any stopped or stuck messages to the bottom right-hand queue manager, because you've said we need to get them all to the same place. So those messages we can't reallocate. We have to leave on the transmission queue until that queue manager comes up. If you've said bind not fixed, that means you don't mind which queue manager these messages go to. Therefore, if any messages are stuck on the transmission queue when we lose a queue manager, the queue manager on the left can detect that and go, well, those messages were going to be going to the top queue manager. Now, because they're bound not fixed, I can send them to the bottom queue manager instead. So those messages can get transferred across and processed by the service. So if availability is important to you, one thing you need to consider is that bind type. Try not to bind on open. If you bind on open, you've locked yourselves in and possibly reduced the availability. Next thing to look at is those messages that are locked on that top left-hand queue manager. In MQ, if a queue manager is unavailable, typically the data or the messages on that queue manager are locked away until you bring that queue manager back up and running again. The only instance really is shared queues on Zeos, in which case you have other options available to you. But if we ignore that for now, and this is just a normal queue manager, the only way to process those messages is nothing to do with MQ clusters. It's all about getting that queue manager back up and running as quickly as possible. Now, that could be using an HA cluster, it could be using multi-instance queue managers, it could just be going in manually and restarting the queue manager, or restarting the system. Obviously, each of those have different things to consider, and also different speeds of getting up and running again. But the essence here is just to realize that any messages locked on that particular queue manager, you need to get that queue manager up and running somewhere, even if it's not in the same place. On that note, if you're, say, using multi-instance queue managers, which you may be familiar with, that means that queue manager can run on of two possible different systems. Those two different systems have different IP addresses. If you're in an MQ cluster, you're quite welcome to use multi-instance queue manager for any queue manager in your cluster. You just need to make sure that the channel definitions, your receiver channel, with its con name in, references both of those IP addresses or both of those host names. Right, once we've got our queue manager back up and running, those messages can be processed just as if it had never failed. But first off, any messages waiting to be transmitted, they can go, so the replies are off. But the messages on the actual request queue, that service needs to be up and running again. So you need to make sure that that service is sat there trying to reconnect, or maybe you're running inside an application server or something like that, where the JMS resource adapter is already doing that reconnect logic for you. But the point is that service needs to reconnect, and then it can process the messages and they can get on their way again. So this is a combination of, yes, using multiple queue managers with multiple instances of the same queue to allow you to reroute messages to an available instance, but you do also have to get any down queue manager back up and running for you to be able to process any one particular message. So that previous one was looking at what happens if a queue manager is shut down for any particular reason. What happens instead if it's the service application here that goes down? If we're processing messages as we were before, quite happily doing that, and then we lose the instance of the service, but the queue manager stays up and running, what's going to happen in this situation? Well, actually, the left-hand queue manager isn't aware that the service has gone down, because it's basing its liveness effectively on the channel connectivity between the left-hand queue manager and the two right-hand queue managers, and that is still up and running and quite healthy. So when messages come through, it's going to continue to workload balance them, and all the messages going to the top queue manager, they're just going to start to build up because no one is processing those messages. Eventually you're going to fill the queue, which may start filling dead letter queues, it might bring channels down, it might do all host of nasty things to your system. So how do we solve this particular problem in MQ clusters? If we roll back, get it back to how it was before, we're going to need an additional setup here. We provide a sample monitoring service that can sit and monitor your queues in your cluster. Now, you deploy it to each of your queue managers where you host these queues. The service is called AMQSCLM. You'll find it in our samples and our tools directory of your installation, and you'll also find it in the manuals and documented what it does, but I'll just show you here. It's basically sat there checking that those queues are currently being serviced. The way it does it is, it really just checks to see whether an application is connected or not, and it has that queue open for input, i.e. it's getting messages off it. It's not smart enough to detect when one goes slower than the other. It's not smart enough just to detect when the queues start to fill up, because that service has become unresponsive. We provide it as a sample, so if you want to put in extra logic like that into your system, then you're quite welcome to do it. But the simple one is just to detect whether that application is connected or not. So it's sat there monitoring this, and what it does is if it ever sees that that application is disconnected, or in fact reconnected, it modifies the cluster configuration of those queues. That goes out to the full repositories and then goes out to any of the queue managers in the cluster that need it. By modifying that cluster configuration, as we'll see in a minute, it controls the workload balancing algorithm, which means it changes the routing of those messages. So let's have a look at what actually happens. We're sending messages, as we were before. We've got rid of replies. We're sending the messages, and we lose our service. Now, we're still sending messages, so there's a chance some messages are going to slip through and arrive on that top queue manager even when that service is not running, because the monitoring service is just effectively polling, or in a period, it's checking the state. But let's say it's now checked the state. It detects that the application is not connected. It's going to do a couple of things. First off, it's going to modify the configuration of that queue. It's going to say, this queue, from a cluster point of view, is now not as attractive as that bottom queue. Which means now, any further messages sent in to the left-hand queue manager, based on that configuration, is always going to prefer to send messages to the bottom queue manager. It's using an attribute on the cluster queue called CLWL PRTY. That's cluster workload priority, if you're familiar with it. But by modifying that, dropping down the priority of the top one, leaving the bottom one high, means that messages will actually go to the bottom one over the top one. So that deals with all new messages coming into the system. What about those messages that are sat there on that queue that slipped through before we detected it? Well, we can also run this monitoring service in a mode that says, actually, if any messages do get through, and I don't have a service attached, I want you to pick those messages up, and I want them to drive them back through the system. Driving them back through the system means we're actually going to send them down to that bottom instance of the queue, because we know that one's got a service attached. So here, we can run a system so that if you lose one of your services, we'll also make sure that we intelligently route the messages to the remaining services, and we'll also pick up any ones that slip through the net and get them down to that bottom queue manager. This solution is good if those services are running in a sort of steady state mode. So they're normally connected, they're normally attached, and only in the event of failures do they detach. So it's not good where these services are coming and going all the time. If they're coming and going all the time, then the monitoring service would have to try and keep up with that, and that could actually put undue stress on the clustering infrastructure of being able to keep up with those changes. So we've looked at service failures and server-side failures. Let's look at what happens with client failures. So, because this is also a part of the solution, we could lose that queue manager on the left, in which case the client can't attach anymore. So this again isn't particularly specific to clustering, but basically you want to have multiple points that client can come into. And now it can choose whether it normally prefers one over the other, or it's randomly picking between the two for workload balancing. Now, the thing from a clustering point of view is no matter which one you pick, say we're going to pick that top one, when it sends messages through, they could get workload balanced to either of those services, but when a reply message is sent back, it knows which one to send it back to, because it wants to send it back to the same queue manager that the client is attached to. So typically, and you can do various configuration things and application things to override this behavior, but typically when a message gets sent through, then it's going to tell the receiving queue manager where that message came from, and that's where the reply is going to go back to. Right. Let's move on to another situation, which we're referring to as a location dependency. So this is a scenario. We've got two systems. Say we've got one in the US, one in Europe. So they're geographically dispersed. We've got effectively the same service running in two different data centers, New York and London. Messages can be processed coming in from other queue managers that are distributed across the globe, maybe in other European countries, other locations in America. And they could be processed by any one of those four instances of a service running on the right-hand side. However, really, we're the opposite sides of the Atlantic, so what do we want to do? We really want to get messages processed to our local data center. That gives us improved performance, lower latency. So that's our normal running system. However, If we have a problem with our data center, so we have a problem with London, all the systems go down, what do we want to do? In that situation, rather than just saying, those queue managers in Europe, sorry, you can't process messages anymore, we want to route those messages via our remaining data center in New York. Okay, it might take a little bit longer, but it is actually still going to result in those messages being processed. So that's what we want to achieve. So how do we achieve it with a cluster? There are a couple of ways to set this up. Let's first of all look, how would you do this in one cluster? So we've simplified the picture a bit, and we've overlaid a single cluster. Because once you've got a cluster, you've sort of given up control over where your messages are going to go to. So this is a way of putting some of that control back in again. So we're going to do this preferred routing using some aliases to map the messages to. And we're going to use the cluster workload priority attribute again. We saw that a minute ago in use when we were talking about service availability, but here we're going to use it again. So we define our alias. We've got a request queue defined in New York and in London. We define an alias called NYQ, so that's our New York queue, pointing to that request queue, and this we're going to put into this one global cluster. And we give it a high priority as well. Then we define the same alias called NYQ, so it's a New York queue alias, but this time we define it down on the London queue manager, which is slightly strange, but you're going to see what we do here. We put it into the cluster as well, but this time we give it a low priority. So we've got a high priority version and a low priority version. Then, over on the left-hand side, we're going to define ourselves a local alias from the queue that the client is sending messages to, and we're going to map that on to target the NY queue. So this is on a US or American queue manager over on the left-hand side. So we've got app queue is pointing to NYQ. Now, in this mode, when both the New York and the London queue managers are running, a client is going to send a message to app queue, it's going to be mapped to NYQ, it'll see both instances of NYQ. One of them will have a priority of 9, one of them will have a priority of 4. In that situation, it will always pick the priority 9 one if it can get a message there. So if the channel is up and running between the queue manager on the left and the New York queue manager, it's going to say, well, that's got the highest priority and I can get to it, therefore I'm going to send my messages to it. And it's going to ignore the priority 4 ones. Unless it can't get messages to the priority 9 New York queue manager, in which case it'll say, well, I can't get to the 9, what's my next available best priority, next best priority, and it'll come down to this London one at priority 4, and it'll start routing messages straight to London instead of the unavailable New York queue managers. So that's how we do messages in the US. Then we set up the mirror configuration for a London queue alias, where we put a high priority down on the London queue managers and a low priority up on the New York ones. And then any of our European queue managers over on the left-hand side, their alias for app queue, instead of being to NYQ, is to LUNQ. So that's actually going to send messages to the alias which has got a high priority down in London and a low priority up in New York. And this is how you can have the same application running on a US system or a European system. It can address messages to the same target queue, which is app queue in its case, not knowing where it's running, and then the infrastructure is going to route the messages intelligently to its preferred location. We could do this with multiple clusters instead of a single cluster. There's nothing much between the two from a performance point of view or a runtime point of view. It really comes down to your style, how you prefer to set up your systems, also maybe how many queues you're routing. The previous example needed aliases set up for each individual queue. This model here, which if you get to the actual slide material, you'll find some notes information on SlideShare. Tells you how to configure this overlapping cluster solution using channels, and we use the same priority, the CLWR priority, but this time we use it on the channels rather than the queues, in which case we prefer to send it based on the channel availability. So this one is a bit more complicated from a point of view of you need 2 clusters, but it's a little simpler in execution in that you don't have to add in extra aliases every single queue that you want to route in that way. So it just gives you choices. Right. Next we're going to talk about avoiding interference. So what do I mean by that? So when you've got a cluster, you can sort of think of the transport of the messages as going through a big pipe where you have little control within a cluster of that pipe or transferring those messages. So if you've got a complicated system, lots of applications doing different things with different types of messages, so you've got some real-time messages, you've got some big data transfer messages, you've got some audit events. Each of those different types of messages need to get through at different speeds with different implications of if they don't. And some you just want to get through eventually, and maybe they're going to be big and bulky, and you realise that those are going to interfere with getting the smaller, quicker messages through. Now, if you're doing that over a general purpose set of queue managers where all these applications can connect into, and those queue managers are in one big cluster, like I said, it's a bit like a pipe. All the messages are going to just get mapped onto their target cluster queues. It's going to be down to the cluster, which has got a channel defined for each queue manager, and it's going to use that channel to send those messages over. So they're all going to mix up on the channel, and some are going to get blocked behind others, which may not be what you're after. Even if you define multiple channels for a particular queue manager within a cluster, which you can do, multiple cluster receiver channels for the same cluster, then you still haven't got any control at that point over which one MQ will pick to send each individual message. So how do you get around this? One way is to, instead of having one cluster that all these queue managers are a member of, define multiple clusters. So we've got 3 clusters defined here. Each of the queue managers is in all 3 of those clusters. Any one queue manager can be in as many clusters as it wants. You just have to define the different channels to say which clusters they're a member of. So now you're in multiple clusters. Don't use cluster name lists to share channels across those clusters. Have a separate channel for each cluster. So each queue manager defines 3 cluster receiver channels and says each of them is for a different cluster. Now, when you define your queues to send your messages to, you can pick which cluster you want to advertise each of those queues in. So your real-time message queues, they would go in one cluster, your batch message queues would go in a different cluster, and your audit event messages would go in a different cluster. Which means when messages get targeted to them, they'll get mapped to the queue, which maps to the cluster, which ultimately maps down to which channel to use. So by having those multiple clusters, you've now got some way of categorizing your queues based on what type of messages they are, and therefore MQ can route accordingly over the correct channels. Let's have a look at another type of interference that you can see in MQ clusters. If we look at this scenario, it looks pretty much similar to the scenario we had before, where we've got clients sending messages to service applications. But here we've got 2 different applications. We've got application 1 and application 2. And over on the right, you can see that application 1, where we've got service 1 processing the messages, is doing that over 2 instances of Q1. Whereas service 2, maybe that's a smaller application, is only going to be doing it for 1 instance of the queue, and that's only going to be on one of the queue managers. So we've got an unbalanced set of queues receiving those messages. Now, applications are sending those messages in randomly for the different queues receiving on the other side. That's all very well, apart from the workload balancing is actually done at the channel level rather than the individual queue level. So what does that mean? So say we sent in 100 messages for application 1 and 50 messages for application 2. Now, they're all going to go through that left-hand queue manager, so we've got 150 messages. And that can see that it's going to be able to send messages to the top right-hand queue manager and the bottom right-hand queue manager. And it's going to try hard to balance them evenly across the 2 channels that it's going to be using. Which means it's going to manage to balance 75 messages, maybe on average, across those 2 instances, those 2 channels. Which means the receiving queue managers each receive 75 messages. So nice and balanced at this point. However, if you then look at what's actually arrived on the individual queues, to achieve this, 50 of those messages on that bottom queue manager must have been going to queue 2 because they're the only place that those messages could go to. Which means you've ended up with a split of 25 of the remaining messages have gone to queue 1 on the bottom right-hand queue manager, but 75 messages have gone to the top instances of queue 1 on that top queue manager. So for queue 1, you may have hoped for a 50-50 split, but what you've actually ended up with is a 75-25 split because MQ has been trying to balance the channels rather than the individual queues. Again, how do you get around it? Well, really to get around this, what you'd need to do is you'd need to separate out Q1 from Q2 at the cluster level. So you have two different clusters. If you've got two different clusters, you can have separate channels, as we saw on the previous slides. If you've got separate channels, the left-hand queue manager will balance based on the channels, and then you'll get a nice even split depending on which cluster you put your different queues into. Or if you really want to get into it, and you could write yourself a cluster workload balancing exit on those queue managers to have a bit more sophistication in it. But that comes down to logic specific to your implementation. While talking about transmitting messages, let's touch on cluster transmission queues. From day one, sending messages from any one queue manager to any other queue managers in a cluster or different clusters was very simple. Each queue manager had a single cluster transmit queue. So that was system cluster transmit queue. All the messages going down any cluster channels would go onto that transmission queue and then off again to the different channels. This poses a number of complications or problems in that it makes it hard to separate out your message traffic. We've been talking about interference there on the channels, but how do you separate them out on transmission queues? For example, if you've got one queue manager and your cluster goes down and we've got messages being sent to there, could those messages that are going onto a transmission queue back up to a point where the whole transmission queue is now unavailable for any new messages going to any member of any cluster? Also, how do you detect those sorts of situations? How easy is it for you to be able to see that messages are building up for a particular channel rather than just building up in general? Typically people do this looking at the depth of transmit queue, depth of messages on a transmit queue. It's harder to do where that transmission queue is being used for multiple channels. Similarly for monitoring, also controlling different limits, different behavior for the different transmission queues. Finally, performance can be impacted by a single transmission queue. If you're really hammering it, if you're really sending in high amounts of, say, non-persistent messages, then there can be some contention on that single queue just trying to process those messages. But it's not normally a primary concern, but that we have seen that in some situations. So, in version 7.5 on distributed platforms, or most of the platforms, and in version 8 on Xeos and IBM I, we've allowed you to split that out into multiple transmission queues, so that now different messages for different channels can go onto different transmission queues, allowing you to improve how you monitor, how you manage it, and potentially your performance. So let's quickly just look at how you do this. You've got two modes. One is an automatic mode, where you basically say on the queue manager, there's a new attribute of a def CLX queue, so the default cluster transmit queue. If you set that to channel, it's saying for every individual cluster sender channel that I create on this queue manager, I'm going to use a different transmission queue. So that's ones whether either you manually configure the cluster transmit queue, say it's to a full repository, or it's auto-generated on the basis that this queue manager needs to send some messages to another queue manager in the cluster. So we've got channel A comes along, at which point the left-hand queue manager automatically will create you a channel A transmission queue called system cluster transmit and then the name of the channel, and that's where all the messages for that single channel are going to go onto. And any additional channels that come along each get automatically their own transmission queue, and the queue manager will clean those transmission queues up as well when they're no longer needed. So that's the automatic mode. Obviously, if you've got lots and lots of channels, you'll end up with lots and lots of individual transmission queues. Alternatively, you can have a bit more control over it, and you can manually say which channels are going to use which transmission queues. So a bit like you would in the non-clustered channel way. You do this on the sending end of the channels. On that queue manager on the left-hand side, you define a local queue of usage xmit queue, so as if it was a normal transmission queue, but you set the attribute of clch name, so cluster channel name. And here you can give it the name of a channel that you want it to use specifically for this transmission queue, or you can give it a pattern using asterisk as the wildcard at any point in it to say actually any channels that match this naming convention are going to use this transmission queue. So say we set up two transmission queues called the pinks transmit queue and the green transmit queue, and we set them up to say we either want all channels that start green to use one and all channels that start pink to use the other. Now, if we've got a good naming convention for our channels within our clusters, and say we've got a green cluster and a pink cluster, then all our channels are named accordingly. And this simple configuration means that all the channels for each individual cluster are going to use a separate transmission queue. So you haven't got a separate transmission queue per channel here. We're using the pattern matching to group them together effectively based on their cluster name. Worth pointing out that any channels that don't fall into that naming convention then fall back to this default cluster transmit queue setting on the queue manager. Do I then use the single system cluster transmit queue for all the ones that don't match, or do I automatically generate a unique one for all of them instead? So you can mix and match these two behaviors. Right, finally, talk a little bit about disaster recovery. So it's not about using MQ clusters to give you a disaster recovery solution. It's more, what do you have to consider if you're using MQ clusters and you have a DR setup? Everyone seems to do it slightly differently. Some things are easier than others, some things are more complicated to do. But you can typically get MQ clusters to fit into most of these setups. We're just going to have a look at those as we go through. First one, synchronous replication. So we've got two data centers over here on the right, data center 1 and data center 2. And we're doing synchronous replication between the two. Now, synchronous replication effectively means any failover from data center 1 to data center 2 is a bit like you turn it off and then you turn it back on again. There's no loss of data, there's no gap in the knowledge of these systems because they're synchronously being replicated. So if we do have a failure and we fail over to data center 2, it's a bit like we're bringing up the same system. So here, the only thing to consider, if we've got queue managers over on the left which aren't inside those data centers, which are within clusters that are communicating with those queue managers in the data center, they just need to be able to connect to them. Now that might be using some network layer that switches the IP so that it goes from data center 1 to data center 2. That's the most typical thing. You could be using comma separated lists, a bit like you would for multi-instance queue managers, to say all these queue managers could be running either in location data center 1 or data center 2, but that's probably less likely. The point is, this is quite simple to do because all you're doing is really moving the queue managers from one place to another. There's no loss of knowledge or state in doing that moving, which is different to the asynchronous replication that we're going to look at now. If we've got the same setup, but this time we're doing asynchronous replication. So if it's asynchronous replication, that means data center 2 is slightly behind data center 1. It could be very far behind, depending on how you're asynchronously replicating, or it could be as little as a few milliseconds that these queue managers are, the knowledge of the queue managers when they're running in data center 1 are compared to the information held or replicated across to data center 2. But it does mean that if data center 1 goes down and data center 2 comes up and starts running the same set of queue managers, you've effectively jumped back in time. All the messages that are on those queue managers have potentially moved backwards. For the queues that you're using in your system, you might have lost the most recent updates, or you might have adding queue messages or even taking messages off them. So that's something for you to consider from a DR point of view. But it also affects clustering, because cluster state is data held inside these queue managers. It happens to be messages on queues as well, but that's sort of irrelevant. The point is each queue manager in a cluster holds some state about what it knows about in the cluster. And by moving from Datacenter 1 to Datacenter 2 with asynchronous replication, that state could have gone back in time. Now, if it's gone back in time, you need to somehow bring them back up to date with the other queue managers in the cluster, the ones that haven't failed over. The way you do this is to use refresh cluster. Now, we normally warn against using refresh cluster because you only really need to do that in light of specific problems where possibly MQ support actually advises you to do it. In this situation, where these queue managers have jumped back in time, you have to use refresh to renew all the information they know about, all the information that they push out to the system. So you have to do that for every queue manager that has failed over in this system. Also, it's worth saying, when you fail back to Datacenter 1, potentially, from Datacenter 2, you've got to do a refresh as well to bring everything back in line again, back in the old data center. So you must do this cluster refresh. Now, in the picture as we've got drawn here, we've got a full repository that's failing over. Now, with a full repository that fails over, with asynchronous replication, you've still got to do this refresh. If you've got to do a refresh on a full repository, that's effectively destroying everything it knows. So you've really lost the benefit of having a full repository there, because it's going to start afresh. It's going to go back to sort of day one, not know anything about the cluster, and have to learn all over again. So maybe rather than failing over your full repository queue manager, just rely on the fact that you have two different full repositories, you keep them separate, and those two different full repositories are effectively your DR solution. So how do we do that? Well, maybe if we look at in the green boxes here, that's what you're actually replicating. And rather than having the full repositories in that set, move the full repository out of the replicated data. You can leave it in Datacenter 1, and you might as well take advantage to take the other full repository and put that in Datacenter 2. Now here, A and B are normally running in parallel, continually, so they're both up to date. But if you lose Datacenter 1 completely, you've lost full repository A. Now, you've still got full repository B. If you've got full repository B, your system can still function quite happily without that first full repository. Also, you've now got the benefit that you don't have to initiate a refresh on that full repository when you do your failover. So you avoid that complication. Finally, we'll look at a DR situation where you don't do replication. Now, some may argue whether this is DR or not, but a lot of systems are set up in this way. Basically, it's a way of being able to run all your services in your different data centers, even if you don't fail over the individual messages, the actual data that's being passed around them. In this situation, it's very, very similar to that New York, London scenario that we looked at earlier, in that we have different queue managers running in the different data centers, but the ones in that data center 2, they're not normally in use because we're using something like cluster workload priority that we used before, or we could be using cluster workload rank as well. Now, rank is very similar to priority in that we'll always send messages to the higher ranked instance of queues or channels within a cluster. The difference is that priority routes dependent on whether the channel is available to the different targets where you have different priorities. Rank doesn't take the channel liveness into account. So if you're using rank, you would actually effectively manually do a switch from data center 1 to data center 2 by switching the rank of your relative queue managers. Priority, it would do it dynamically based on detecting that the channels have gone down. Now, some people want to be able to dynamically route in the event of a failure. Other people want to have more control. That's where you might want to use cluster workload rank instead. bearing in mind that in this solution, no matter what you use, any messages that are on the queue managers in the failed data center, those messages aren't going to be available until you bring those systems back up and running. And that brings me to the end. So we've gone through the different aspects, how you can use clusters to solve some of your problems. Hopefully that's been of use to you. Thank you very much.